Hello and welcome to the lecture this morning. We are live from Niger, Iyenu. Good morning, everyone. I hope you are enjoying yourself at your holiday. Make sure you are reading. Okay, let's take off this morning. Please go ahead and invite your friends, call your friends, let them come online. We are live online. Call your friends, let them come online. We are live this morning. Physics 101. Call your friends, call your departmental classmates, let them come online. In a few seconds, we'll take off. Okay. I hope you are all good. Get your writing materials. Get your pen. We're about to take off. Okay, quickly this morning, we are looking at Newton's laws of motion. Newton's laws of motion. Newton's laws of motion. Now, a kind of a background for you to understand the Newtonian mechanics. We have to look at what motion is all about. And we all know that motion is the change in position of an object or change in the position of a body with time. So change in position of an object or a body with time. So when they move from one point to another point, we say that motion has taken place. Now, and you find out that there are many types of motion. We have translational motion, like you all know. If you did your SS1 very well, you all know all about all these things. So translational motion, rotational motion, vibratory motion, or oscillatory motion, random motion. These are types of motion. However, motion in general, what causes motion is called force. Now, force is an agent of motion. So we all know that in force can cause motion. Now, to that effect, so Newtonian mechanics now came up. And a man called Isaac Newton came up with a lot of theory that later was propounded into a law. And one of the laws that we're going to look at today. So we are looking at Newton's law of motion. And number one of it is called the first law. So Newton's first law of motion. So get your writing materials ready. We are moving. So Newton's law of motion. So the first law states that when the net force acting on the body is zero, its motion does not change. So you see, the net force acting on the body, when it is zero, now it says that its motion does not change. I know many of you are not familiar with this, but let me state the one that you are familiar with. The Newton's first law of motion. It states that every object or body continue in its state of rest or uniform motion in a straight line unless it is acted upon by an external force. So that is Newton's first law. You know, you have entered university now. So we are playing at a higher level. So we are working with the first one that states that the net force on the body is zero. So it says that its motion does not change. And to that effect, We'll be looking at some mathematical equation that shows this, that the net force acting on a body is equals to 0. So therefore, now let me just throw a little light on the one that you know, that is being acted upon by an external force. Now we know that external forces like pull, like push, like tension, as in these are contact force. So this contact force, when they make contact with a person or an object, so you find out there will be a change. So, and that change now introduces what we call force that will cause the motion. So, to that effect, the first law that brought about the force acting on the body, the net force acting on the body, that is 0. Let's look at it and see how everything plays out. So now we have summation F. Now, I hope you still remember, like I taught you, now scalar and vector quantities, that force is a vector quantity. So that's why you are seeing those arrows, the arrow on the top. So the arrow shows you that it has a direction. It's not just only magnitude, but it has a direction. So now the summation of this force, which is equals to now the first force acting on the body plus the force 2 also acting on the body is equals to 0. So that's what we are trying to let you know, that the first law states that when the net force acting on the body is 0, it means that its motion does not what? Change. Its motion does not change. Are we together? So its motion does not change. So the summation, the net force, which is summation of these forces, equals to the force 1, the force 2 is equals to 0. Now let's look at it critically for you to find out why it is 0. So that is when we apply a second force, that is the force 2. Now let's look at the force 2. Now, assuming that this second force, which is the force 2, are we seeing it? So the force 2, is now equal in magnitude to that of force 1. That is, it's trying to tell us that F2 is now equals to minus F1. So F2 is equals to minus F1. And to that effect, we can conclude that our summation F is equals to the direction of force 1 now plus into minus the force 1. So this force 1 now is representing the force 2, and they are now equal in magnitude, which is equals to 0. So now when you look at this critically, you'll find out that the force 1 minus force 1 is going to give you 0. Do you understand this? It's going to give you 0. So that's what Newton was trying to say, that the net force acting on a body for the first law is equals to 0. Is equals to 0. So it is equals to 0. So these results show that in Newton's first law, 0 net force is equivalent to no force at all. So 0 net force is equivalent to no force at all. So this is a higher level. For you to drop that your lower level, that everything is being acted upon by an external force. Now that law still holds. However, to take it more further, you have to understand that the zero net force is equivalent to no force at all. So the tendency of a body to keep moving once it is set in motion results from a property that we call inertia. So it results from a property that we call inertia. So the tendency of a body to keep moving once it is set in motion. Once it is set in motion. So a body has to be moving while it is set in motion. So the tendency of that body is what we call inertia. And from the first law, we have to take it a bit deeper to what we call inertial frames of reference. Inertial frames of reference. Inertial frames of reference. Please, I hope you are taking the notes. Please just try to be fast. Inertial frames of reference. So inertial frame of reference. When we talk about reference, we think, now there are many definitions of what reference is all about, but in this aspect, inertial frame of reference, we are talking about position. So, and it's very important that you understand this inertial frame of reference, because that is what will take us further to the second law of Newton. Now, let's look at it. I want to read out something I wrote here, which is going to help you. Now, suppose you are in a bus. Now, you are in a bus. Maybe you are moving from Board Junction to Ogidi, or just making a translational motion. So suppose you are in a bus that is traveling on a straight road. So straight road, and is speeding up. So, for example, you are moving from this roundabout, maybe to another roundabout. It's an express. You have to speed up. So you are in that bus on a straight road. Let's look at what is happening there. So we are considering inertial frame of reference. Now, if you could stand in the aisle, that's in the middle of the bus, as in you are standing up, perhaps you are acting as the conductor, trying to collect money from people. Just picture yourself as that. You are not like that anyway, but just for the sake of this study that we are doing. Now, if you could stand in the aisle on a roller skate, you will start moving backward relative to the bus as the bus gains speed. I believe each and every one of us, you must have experienced something like this before now. Maybe you entered a coaster, for some of us living here, you entered a coaster, moving from one position, perhaps from main market to your destination. You find out maybe, the bus was just rushing, and then you quickly entered, immediately they speed up. You find out that you start moving backwards. So relative to the bus, as the bus gains speed. Are you getting it? Yeah, it's very, very easy. It is called relative motion. In a nutshell, that's what we are talking about. So if instead the bus was slowing to a stop, you will start moving forward down the aisle. Are you getting it? I believe you have experienced something like that. We are looking at inertial frame of reference. That is from your position where you are, the things happening around you. Now, in either case, it looks as though Newton's first law is not obeyed. Are you seeing it? Now, it looks as if the Newton's first law is not obeyed, because you find out as the bus speed up, it looks as if you are moving backward. Now, as it slows down, you are moving forward. So it looks as if Newton's law is not obeyed, because you will not see any form of net force there. So there is no net force acting on you, as in there is no force acting on you per se, as in terms of contact. There is no force acting on you. So you are just being carried, as a result of the movement of the vehicle or the bus, rather. So there is no net force, a kind of contact, a kind of push, a kind of pull, a kind of tension acting on you. So you see, in this case, it looks as if the Newton's first law is not obeyed. Let's keep moving. So because there is no net force acting on you, the point is that the bus is accelerating with respect to the earth. That's what you have to understand. This whole thing is moving because of your geomagnetic pole. So it's moving with respect to the earth, and it's not a suitable frame of reference for Newton's first law. Because no net force is acting on you. No net force is acting on you. When there is a net force acting on you, Newton's first law is obeyed. So this is a kind of relative motion, but it's not relative motion per se. We are looking at inertial frame of reference. That a frame of reference in which Newton's first law is valid is called inertial frame of reference. So a frame of reference where we can say that Newton's first law is valid, Newton's first law is obeyed, that kind of reference is what we call inertial frame of reference, because it has the tendency of the body to keep moving while it is set in motion. That's what you have to understand. While it is set in motion. So this thing that we just read a few moments ago, you'll find out that there is no net force acting on you if you are in that bus. Now, you can try it as a classical experiment. Try it as a classical experiment. Maybe for those of you living in Lagos, you are moving from my to Jota, you can just board a bus, just pretend as if you are acting as a doctor, as the conductor, as the bus speed up. So you understand this thing as a classical experience. So I'm trying to tell you that a frame of reference in which Newton's first law is valid is called an inertial frame of reference. The earth is at least approximately an inertial frame of reference, but the bus is not. Do you understand it? Perfect. So you find out the bus is not an inertial frame of reference, but the earth is. Are we together? Okay, so let's move on. So we'll look at the Newton's second law of motion. Newton's second law of motion. I hope you are right, and I hope you are right, and I hope you are right, and I hope you are getting this thing. If you are getting this thing, start commenting. I hope you are getting this thing. Okay, let's look at Newton's second law of motion. Newton's second law of motion. Newton's second law of motion. So the Newton's second law of motion states that the acceleration of an object or a body is directly proportional to the resultant force acting on it. Wow, powerful. Let me give you some time to digest this. Just a few seconds. That the acceleration of a body is directly proportional to the resultant force acting on it. So for the Newton's second law, we are looking at second law. So we are looking at second law, okay? So looking at the second law, we are looking at the second law of Newton. So the second law. So the second law now. So the second law states that the acceleration of an object or a body is directly proportional to the resultant force acting on it. So that is to say, now, that's to say that summation of the force is equals to MA. This is the one each and every one of you know. So F equals to MA. So you can continue to write that F is equals to MA. Are we together? So F is equals to MA. Now, I hope you still know, now, as we are talking about the summation, now this can act along the x-axis, this can act along the y-axis, this can act along the z-axis because of the acceleration. You know, acceleration is a vector quantity. Now, let me just give you a classical example of what I'm saying. Okay, so we have a summation F subscript x equals M A X. So you see this one is acting along the x-axis. Now we have again summation F of y. So this one is acting along the y-axis. Now it also acts along the z-axis. You can also write that. Now, to that effect, you know, I just gave you a superior one. But let me give you the one that you guys know about Newton's second law of motion. So Newton's second law of motion states that the rate of change in momentum, the rate of change in momentum is directly proportional to the impressed force. So Newton's second law of motion states that the rate of change of momentum is proportional to the impressed force, and it takes place in the direction of force. So it takes place in the direction of force. It takes place, we are still on Newton's second law of motion. So that it states that the rate of change of momentum is directly proportional to the impressed force, and it takes place in the direction of force. So let's look at it now. Now we have that F is directly proportional to the change in momentum. So we have change in momentum. So divided by all over, we have it to be time taken. So we're about to derive the formula now. So F is directly proportional. Now you know that change in momentum is mv minus mu divided by time. Okay? Divided by time. Now, this is change in momentum divided by time taken. Okay? So now, where m stands or represents the mass of the body or the mass of the object, where u represents the inertial velocity, where v represents the final velocity, then t represents the time taken, and F, you know, F is force. Okay, F is force. Okay, are we together? Are we together? Are we together? Are we together? Okay, we are going somewhere. We are looking at something. So please follow me as we teach. So F, now you find out that the m is common there. So F is proportional. Let's bring out the m into v minus u. Okay, divided by time. Are you seeing it? Are you seeing it? Are you seeing it? So divided by time. So divided by time. Now, if you can still recall, in fact, let me write it. You recall, we've done it, that acceleration is equals to V minus U all over T, over time taken. So acceleration represents this. So acceleration is equals to V minus U divided by time taken. Divided by time taken. So from this, our force, assuming we introduce acceleration to replace V minus U all over T. Let's do that immediately. Let's see. So F is proportional to M A. Wow. Wonderful. M is proportional to M A. F is proportional to M A. So F being proportional to M A. Now let's remove this proportionality constant sign, to introduce a constant. So when we do that, let's look at what will happen. So our F will then be F equals K M A, where our K is equals to 1. So our K is equals to 1. So our K is equals to 1, and therefore F is equals to MA. So this is what Newton was trying to explain in his second law, that the rate of change of momentum is proportional to the impressed force, and it takes place in the direction of the force. It takes place in the direction of the force. Okay. Now, I want us to look at just 2 examples before we call it a day. 2 examples. 2 examples. I hope you are getting these things. I hope you are getting these things. I hope you are getting these things. Okay. So let's look at 2 classical examples, and then we'll call it a day. We'll have many of them. Next week we can still continue. So let's look at, one example. Let's play with one example. Okay. So an example 1, an unbalanced force of 20 Newton. An unbalanced force of 20 Newton. An unbalanced force of 20 Newton acts on a 4 kilogram mass. An unbalanced force of 20 Newton acts on a 4 kilogram mass. An unbalanced force of 20 Newton acts on a 4 kilogram mass. What acceleration does it give it? What acceleration does it give it? What acceleration does it give it? So what acceleration does it give it? So let's look at it. Let's look at it. So the example 1, let's play with it. An unbalanced force of 20 Newton acts on a 4 kilogram mass. What acceleration does it give it? Now, let's look at it. We know from the Newton's second law that F is equals to F is equals to MA. Now, we are given that our force is equals to 20. Oh, sorry about that. Okay, let me start again. F is equals to MA. Now, you from the question, we have our mass to be 4 kilogram. Then we have our force to be 20 Newton. So we are looking for our A. Are we together? So we make A the subject of the formula. So we divide both sides by M. We divide here also by M. That when M cancels this M, we are left with A. So our A is equals to F divided by M. Are we together? So let's substitute the figures, which is equals to, so the force is 20 Newton divided by the mass is 4. So 20 divided by 4. When you divide this, it's going to give us 5 meter per square second. 5 meter per square second. 5 meter per square second. 5 meter per square seconds. 5 meter per square seconds. 5 meter per square seconds. Are we getting these things? Are we getting them? Are we getting them? Are we getting them? Are we getting them? 5 meter per square seconds. So where force was given, the mass given, then we are looking for the acceleration. Are we together? Okay, let's keep moving. Let's keep moving. Let's keep moving. Let's keep moving. Okay. Example 2, before we call it a day. So example 2, please take it. Example 2. A 900 gram stone is pushed along a tarmac. A 900 gram stone is pushed along a tarmac by a horizontal force of 20 Newton. A 900 gram stone is pushed along a tarmac by a horizontal force of 20 Newton. Are we together? Okay. A frictional force of 8 Newton. A frictional force of 8 Newton opposes the motion. A frictional force of 8 Newton opposes the motion. What is the acceleration given to the stone? What is the acceleration given to the stone? So what is the acceleration given to the stone? Let's look at it. Okay. What's the acceleration given to the stone? Okay. So what is the acceleration given to the stone? Okay. So now we have here. So the unbalanced force. The unbalanced force is equals to, now the horizontal force, which is 20 minus the frictional force, which is 8, is going to give us 12 Newton. The unbalanced force is now what? Because, you know, we have to get the unbalanced force. And to get the unbalanced force, you minus it from the, you get the frictional force and the horizontal force. You minus the frictional force from the horizontal force, and then you get the unbalanced force, which is 12 Newton. Now we'll move back again, that F is equals to MA. Are we there? Are we there? Are we there? We are looking for acceleration. So we divide both sides by M. We divide by M. Okay, and then we'll cancel M, we'll cancel M, and we'll have that our A is equals to F over M. Are we together? Are we together? Are we together? Are we together? So now having this, we then have our A to be equals to the force is 12 divided by 0.9. And when 12 divides 0.9, we have 13.33 meter per square seconds. 13.33 meter per square seconds. 13.33 meter per square second. Okay. As you arrange your question, we just have a minute to go. As you arrange your question, let me give you something to play with. You know, some of you are playing in the house, you know, and it's not good. You need to get yourself ready. Prepare for quiz. Get yourself ready. Prepare. So I want to give you something to play with while you are playing in the house. So play with this as a home task or whichever one you call it. Now, please write this down. Okay. A 12 kilogram, a 12-kilogram stone is pushed along a tarmac. Is pushed along a tarmac by a horizontal force of 15 Newton. Full stop. A frictional force of 2.5 Newton opposes the motion. Calculate the acceleration. Calculate the acceleration. I said that a frictional force of 2.5 Newton opposes the motion. Calculate the acceleration given to the stone. So calculate the acceleration given to the stone. 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 So when you get to your house, please solve these things. Solve them. It's going to help you. It's going to help you. Play with them. You okay, maybe let me give you also another something to play with. You know, please take this thing down again. An unbalanced force of 200 Newton. An unbalanced force of 200 Newton acts. An unbalanced force of 200 Newton acts on a body of mass 20 kilogram. Calculate the acceleration. 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 Okay, okay. So we are done for today. We are done for today. We'll be meeting again next week. But before we meet again next week, I want to encourage you. Some of you, I know, at home, a lot of chores, lot of home distraction, and all of these things. Pay the price now. Pay the price now so that you will move to the next stage of your life, which is the 200 level. Okay? Thank you. Bye for now. Till next week. Good morning, sir. So you can stop right there. No.